Recall that we have discussed certain laws that govern fluid flow. Okay, and these laws were derived from your balances, whether it's uh, mass balances or energy balances. So we have discussed three of them. Okay, we have the Newton's law of viscosity. Again, it states that the ratio of your shear stress to your rate of deformation or rate of shear is actually a constant, which we know as viscosity. We haven't really had time to emphasize the second of these laws, which is the no-slip boundary condition. But practically, it's the fact that your fluid adheres to your boundary, let's say the walls of a pipe, so that if you put a stress or a force and allowed, let's say, the upper boundary to move with a certain velocity, then that layer of fluid which adhered to that particular boundary will have the same velocity, right? The third law is your conservation of mass, and it's in the form of what we discussed as your continuity principle. Okay. Now there's a fourth law which we will discuss today, and that is from or based on the conservation of energy, and it's in the form of what we call Bernoulli's principle. Okay. So this equation or principle, along with the continuity principle, is very much applicable to fluid flow, whether your flow is in your pipes or tubes, okay, internal, or weathering flow past objects or around objects or bodies, okay? And doing the energy balance will result to what we know as simply as the mechanical energy balance equation. So this mechanical energy balance equation can do a lot of things, like in this piping system, for example, it can calculate parameters such as velocity at any point in the system, or if you want to measure the pressure at any point along the piping system, etc. Or if you want to maybe calculate the power requirement of a certain pump. Okay, so here is what it looks like. We have a pressure term, okay, or it's basically the energy of the fluid that is inherent to the fluid. Okay, of course we have the kinetic energy term, delta U squared over 2gc. So of course the kinetic energy can vary because the velocity will vary. And the reason why velocity varies is because of a lot of things, and one of them is probably change in the, let's say, the diameter of your pipe or tube, or the size or the cross-sectional area. Okay, sometimes it narrows, sometimes it enlarges. Okay, an example would be if, let's say, your tube is reduced to 1/2 the size of the cross-section, okay, or vice versa, or maybe your tube is going, the fluid in your tube, okay, flows, okay, from the pipe to the tank or vice versa. So you will need to expect that there will be kinetic energy changes. So this term accounts for that. Of course, you have your term that accounts for the potential energy of the fluid, and then that happens if you have fluid in with an elevation. Okay. Also, your fluid, you will expect that it will have some frictional dissipation. So it's in the form of this variable F. Okay, and this frictional dissipation could be because of the fluid exerting some friction with the pipe walls, or if your fluid is flowing through certain hurdles such as your valves and fittings. Okay. And of course, you will also need to account for any work done on the fluid, such as work done by a pump. Okay. In fact, one of the things that we can do with the mechanical energy balance equation is to calculate the performance or power requirement of a certain pump if we're given the, let's say, the efficiency of that pump. Okay. Now, if we can, let's say, have the friction term vanish, okay? In other words, there is no friction, the fluid is inviscid, okay? And also let's say that there are no shaft work being done on the fluid, okay? So we're left with three terms of the mechanical energy balance equation. And this equation is also practical. Okay, it can do a lot of things as well. Imagine we have here a section of fluid flowing in this manner. Okay, so the fluid here, okay, let's say, all right, that it's speeding up. Okay, tumataas yung kanyang velocity. And the reason why that's the case is that the fluid here, or the tube rather, it narrows, okay? Lumiliit yung kanyang cross-section or yung kanyang diameter. So you expect, of course, that the velocity and thus the kinetic energy will increase. So the fluid accelerates, okay? But since we mentioned a while ago that we assume that the fluid is inviscid, saan nanggagaling yung kinetic energy na yun? Okay, it should not come from frictional dissipation, because we assume that there are no frictional dissipations, or there's no, let's say, flow along hurdles or whatever. Okay, so saan nanggagaling yung kinetic energy na yon na pagtaas? So it's possible, of course, that increase in kinetic energy that drives the flow from left to right is your pressure, okay, your delta P. Now, yung ano kasi, let's say in this section you have a pressure here, okay, yeah, and this pressure at this point does positive work because it flows along with the fluid, okay. Now, in this section, in the narrower part of the tube, meron ding pressure dyan. Okay? So there's pressure here. Oops. And then may pressure dito. Now, this pressure at this point, it does negative work, all right? Because it the direction or the exertion of the force is against the fluid flow. Okay? So, however, the fluid must speed up because of the narrowing of the cross-section of this tube. So in order for it to speed up, okay, we can therefore say that the pressure here should be larger than the pressure here. So basically, what drives the flow now, of course, is if you need to, you have to of course account for the elevation or the potential energy, but let's say holding that as constant, right? What drives the flow now, or the acceleration of the fluid from left to right, will be your pressure. Okay, so this relationship is only applicable if you have a steady state flow, and the flow should be incompressible. Again, incompressible means no changes in density. And then if the flow is laminar, okay, or streamlined. And we call this relationship as the Bernoulli's equation, okay? Also, I forgot to mention that the fluid should be inviscid, okay? So the mechanical energy balance equation, all right, is used for steady state, incompressible, and laminar flow. But additionally, if your fluid is inviscid, then you have the Bernoulli's equation. Okay, so it can answer a lot of questions in not just in piping system, but also in aerodynamics, for example, or even blood flow in your circulatory system. So for example, if you're asked to, let's say, install a piping system underground that will create like a water fountain over here at this point, okay, by installing, let's say, a 15 centimeter pipe here and a 5 centimeter pipe there bent like that, and there's like an elevation of the fluid when it comes to this point. From that point, it's an 8-meter elevation. Okay, and you know that the pressure here is atmospheric, and if you can measure the velocity of that fluid here, which is in this example 32 meters per second, you'll be able to calculate what amount of pressure is needed, okay, at this point in order to drive that fountain, okay, water fountain or fluid flow. But let's apply this equation in the in a more biological scenario. Okay, an example is the case wherein we pass out, right? So why do we do that? Why do we pass out? So it turns out that, of course, if you're standing, okay, let's say you have your heart, okay, from the aorta up to the cranium or the brain. So there's an elevation of around 30 to 40 centimeters, depending on your height, of course. And the blood vessel from the heart to the brain. So you have that, okay. Sometimes we can assume that the diameter is constant, sometimes not. Okay. Anyway, let's say that for some reason nag-decrease yung flow, okay, from the heart to the brain. So that's the reason why we pass out, right? Kasi we evolved, all right, so that kapag nag-pass out ka kasi, so what happens is that nagiging horizontal na lang yung flow, right? So you can eliminate the potential energy term in your Bernoulli's equation. So what's left is the pressure term and perhaps the kinetic energy term, okay? So in that case, magkakaroon ng increase in blood flow from the heart to the brain kasi na-vanish na yung yung potential energy term. Alright? So maybe we can answer this problem. So there's a blood flow from the left ventricle into the aorta, which can be modeled as a reducing nozzle. Okay? So if we know that the left ventricle has a diameter of 3.1 centimeters and the aorta is 2.7 centimeters, okay? And the pressure is given. In the left ventricle, it's 130 millimeters mercury, and the pressure in the aorta is 123 millimeters mercury. Blood is ejected from the left ventricle at a speed of 120 centimeters per second. So yung blood nagagaling sa left ventricle, okay, with that given velocity. Let's calculate the difference in height between these two locations. So let's take the density of the blood to be 1050 kilograms per cubic meters. Okay, so if you're going to sketch the problem, you have the left ventricle and the aorta. Okay, so what we're after is the difference in the location, okay, of these two. Now it's a given in the problem that the blood ejects or flows at this point in your left ventricle at a velocity of 120 centimeters per second. Okay, and you're also given the sizes or the diameters of both locations. For the left ventricle, it's 3.1, and for the aorta, it's 2.7. Okay, 2.7 here. Okay, let me write that down. 2.7 centimeter. And here it's 3.1, right? 3.1 centimeter. Okay, so let's use the mechanical energy balance equation. Okay, so this is the equation, but let's assume that the flow or the fluid is inviscid, so there are no frictional dissipations. And let's also neglect any work done on the fluid. Of course, there will be some because probably the heart, okay, could act here as a pump and it sort of pounds on the blood, giving it some work. Anyway, if we do these cancellations, we will arrive at, again, the Bernoulli's equation. Okay, so let's proceed. Let's go through each term one by one. So starting with the pressure term. Okay, so for the pressure term, it's delta P divided by rho. Now, I designated here the left ventricle as 0.1 and the right, and the aorta as 0.2. Okay, so delta P is basically P2 minus P1 over the density. So P2 is 123 millimeters mercury from the problem, while P1 it's 130 millimeters mercury. The density is 1050 kilograms per cubic meters. This is the density of your blood. Okay. I need to convert millimeters mercury to a metric system unit. And we have here, of course, Pascal. So the conversion is right there. And you do that, it turns out that delta P over rho is negative 0.889 joules per kilogram. Okay. So each term here will result to a unit of joules per kilogram in the English or in the metric system. Now let's go to the next, the kinetic energy term. Okay. So for the kinetic energy term, delta U squared over 2gc. Delta U squared means U2 squared minus U1 squared over 2gc. Okay. We know what U1 squared is. Okay, so it's 120 centimeters per second. However, we need to find U2. Okay, so how do we do that? We can use the continuity equation. Again, on the assumption that the flow is incompressible. And of course, it will always be an incompressible assumption because you're using here the Bernoulli equation or the mechanical energy balance equation. The assumption will always be incompressible. Okay. And remember from your continuity equations, the mass flow rate entrance is equal to the mass flow rate exit, or M1 equals M2. But since it's incompressible, it becomes Q1 over Q1 equals Q2, or the volumetric flow rate entrance equal to volumetric flow rate exit. Okay. Now, volumetric flow rate is expressed as U times A, velocity times area. Take note that I'm using the variable U here instead of V. Okay. So that's the relationship. Now, we know U1, but we want to know U2. Tama? So, expressing that, okay, U2 will become U1 times A1 over 8. Now, A is just pi over 4D squared. We have D2 here, we have D1 there. You can just cancel this constant such that it becomes U2 equals U1 D2 over D1 squared. So, plugging in the values, U1 is 1.2 meters per second because it's 120 centimeters per second. D2 over D1 is 2.7 over 3.1. We know this given from the problem. Squared, I don't really have to convert centimeters to meters because it's a ratio and they just vanish. So the result will be 0.91 meters per second. So that is the velocity at that point 2. Going back to the kinetic energy term, okay, again, U2 squared minus U1 squared over 2gc. U2, we know that already to be 0.91. Squared minus U1 is 120 centimeters per second squared over 2 times 1. Okay, and you will have negative 0.31 newtons per kilogram. Now, going back to our working equation, which is the Bernoulli's equation, okay, plugging in the values we have calculated already. The pressure term is negative 0.889. The kinetic energy term is negative 0.31. Delta Z is what we're looking for. We're looking for the height difference, right, between the 2 points. G over GC is 9.81. So therefore, we can calculate delta Z or the height to be 12.2 centimeters.